In this video, we'll finally look at the expression for the derivatives of the loss function with respect to the parameters in our neural network. So we're finally ready to get the expression for the gradient of the loss function with respect to the parameters that we need to apply the stochastic gradient descent algorithm for training a neural network. So let's first look at the partial derivatives with respect to the weights. So assume we are looking at the partial derivative for the weight ij for the hidden layer k. So we want the partial derivatives of the loss function. Now, the only pre-activation that depends on this weight is going to be the pre-activation at the hidden layer k for the ith hidden unit. So wij or kij is going to connect that hidden unit with the hidden unit below and using its activation for the jth hidden unit at the layer below. So using the chain rule, we can write that partial derivative as the product of the partial derivative of the loss function with respect to the pre-activation at the kth hidden layer for hidden unit I times the partial derivative of that pre-activation with respect to our parameter. And now we know that the pre-activation is a linear function with respect to the weight. So it's a linear transformation of the activation of the hidden layer below. And now in this sum, so the gradient with respect to wij for the kth hidden layer of this term, the bias is 0. This does not depend on the weights. And here we have a sum that involves a bunch of different weights, but the only one that matters, that involves wij, is the one for the value of j that corresponds to this j here. And so here then we'll have this parameter, so the parameter multiplied by the activation of the jth hidden unit at the layer below. So if we take the derivative of that with respect to wkij, we just get the activation value. So this is just equal to the activation of the jth hidden unit in the hidden layer that's just below, the hidden layer k minus 1. And now, so we just take that and we multiply it by the pre-activation partial derivative, which we've seen before. We've seen how to we've seen the formula for. Okay, now what if we want the gradient? So if we want the gradient with respect to a matrix, then that's going to be, instead of being a vector of partial derivative, it's going to be a matrix of partial derivative where the element ij is going to be the partial derivative with respect to wij for the kth hidden layer. Now if we go back in the expression, we see that this partial derivative for elements at row I and column j is just a multiplication of the pre-activation partial derivative for neuron I times the value, the activation value of the neuron for the jth neuron at the layer below. So what we can do is take the vector of pre-activation gradients. So that's so the gradient vector is going to be the vector of partial derivatives for all potential pre-activation in the layer k, and then multiply that by the vector of activations at the layer below. But we're going to transpose it to get a row vector. Now if we take a column vector times a row vector, we're going to get a matrix, and the element at position I, row I and column j is simply going to be the ith element of the column vector times the jth element of the row vector. And so indeed we'll get a matrix where the element ij is going to be the multiplication of the ith element of that vector times the jth element of that vector, which turns out to be the actual value of the partial derivative with respect to connection ij. So we get this expression actually does correspond to the gradient with respect to the full matrix W for the hidden layer K. And now we can look at the partial derivatives with respect to the biases. So again, the only pre-activation that depends on the IF bias for the hidden layer K is going to be the pre-activation for hidden layer K looking at its IF hidden unit. So we can take, with the chain rule, that partial derivative times the partial derivative of that pre-activation for the IF hidden unit, hidden layer K, with respect to our parameter. And looking at this formula, we see that this term does not depend on the bias, but this term depends on it. And it's actually just that variable. So if we take the partial derivative with respect to that, it's going to be 1. So this term multiplied by that just essentially cancels out because it's equal to 1. So we only get the value of the partial derivative of the pre-activation for the IF hidden unit. And if we put that into a vector, well, that's just the gradient for the pre-activation. So actually the gradient for the bias for the hidden layer K is just the gradient for the pre-activation. So it's actually very simple. So with that, we have an expression for the gradients for all of our weights and all our biases that we need to use to apply stochastic gradient descent training of neural networks.